Hello everyone. In this lecture, we're going to start looking at arithmetic with complex numbers. So, we saw that complex numbers are to be treated like polynomials, a plus bi. I is like the variable of the polynomial. It satisfies the special property called I square equals minus 1. And that's all you have to remember for arithmetic. As long as you keep that in mind, arithmetic will be very, very smooth. And let's see how that works. Okay. The first thing is equality. When do we say two complex numbers z1 and z2 are equal? z1 equals z2. That happens if and only if real part of z1 equals real part of z2 and imaginary part of z1 equals imaginary part of z2. It's an easy enough thing to say. Z1 has two numbers a plus bi, z2 has two numbers inside two real numbers and it's c plus di. And when are those two equal? When both a equals c and c equals d. So that is one small thing. And then for addition and multiplication, we simply treat a plus bi as a polynomial in I and use a special thing that I square equals minus 1. I itself we leave alone, I is okay in the answer, but any I square that I have, I'll replace it with minus 1. Okay, so here's illustration. You can see very easily how that works. So if I have to add a plus bi and c plus di, it's like terms, no? How do you add polynomials? The like terms we take as common and then we add b plus d. So that's all we do. The two constant terms, so to speak, the real part add separately and the imaginary parts add separately b plus d and then times I. So it's as simple as that. And then multiplication, once you remember the polynomial rule, it's very, very easy. A plus bi times c plus di. How do you multiply polynomials? You multiply a with c, a with di, bi with c, and then bd, bi with di. Okay, so this is what you get. Now you notice that this I squared, right, is actually minus 1. Okay, so this part actually becomes real, bdi squared. So once you have this being minus 1, this and ac, right, these two are the real parts. So and you can combine those two and do ac minus bd. Now these two have I in them. That's imaginary part. So ad plus bc times I. Okay, there's no reason to mug up this formula by heart. This multiplication just follows polynomial rules. It's very, very simple to remember, except you have to keep remembering this I square is minus 1 always. Okay, so excuse me. So here are some examples. I don't want to go through them in detail, but you can see quickly how these examples work in various cases, how you go through and multiply and you get the same answer either way. So for instance, things like this, I mean, you might remember this a plus b into a minus b is a squared minus b squared. All of those things work, right? 1 minus I squared worked, but then I squared is minus 1, so 1 minus of minus 1 became 2. Okay, so you have this very nice looking property, 1 plus I into 1 minus I is actually 2. Okay, so these kind of things will happen with complex numbers. So the rule to remember is, any algebraic expression simplification formula, a plus b whole squared, a plus b whole cubed, a cube minus b cube, whatever formula you remember from your algebra, all of those things work when those variables are complex as well. Okay, so that's a nice and simple thing to remember. So arithmetic, addition, multiplication are really, really easy with complex numbers. Okay, so what about things that are unique in some sense to complex numbers? The way you do, so there are two operations which are sort of unique, though it doesn't exist exactly in the same way in the real domain: conjugation and absolute value. And then there is, or division has one slight complexity to it. Okay, so we'll see all of those things next. So conjugation is a special operation. Okay, so if you have a complex number z, which is x plus yi, we denote the numbers conjugate as z bar. Okay, this I'll call it z bar. The line on top of z, that is called z bar, and it's defined as z bar equals x minus yi. If I have x plus yi, conjugate becomes x minus yi. Okay, so this is an operation, like I said, it's only for complex numbers. If for instance z is real, okay, real numbers are also inside complex, right? So if z is real, what does that mean? Y is 0, right? If z is real, y is 0, and then what is z bar? Is x itself. Okay, so conjugation of a real number is itself. Okay, on the other hand, complex number, the conjugate changes. Okay, so this conjugation is something sort of unique to complex numbers in some sense. Okay, so here is a very interesting property of a number time its conjugate. Okay, so you have a number x plus yi, complex number, multiply it with its conjugate. If you multiply with its conjugate, you can simplify this. This is not very hard to see, right? X times x is x squared. yi times minus yi will give you y squared actually. It's minus y squared I squared, that's okay. And then x minus xyi plus xyi will cancel. Okay. Or another way to see it is a plus b into a minus b is a squared minus b squared. b squared is y squared I squared, and that's minus y squared. So minus of minus y squared will become plus. So this x squared plus y squared is real, and not only that, it is non-negative. It's greater than or equal to 0, right? X square is positive. I mean, cannot be negative. Y square also cannot be negative. So x squared plus y squared cannot be negative either. So it's greater than or equal to 0. So the z bar is a positive real number, non-negative real number. It can be 0. Only case it can be 0 is when both x is 0 and y is 0, or the complex number itself is 0. Okay, so the z bar has a lot of very nice properties. It's real. The fact that it's real is important, and it's also non-negative. Okay. Okay, so now this leads to a very nice definition for absolute value. This is also called magnitude, norm, modulus of a complex number. The absolute value of z is denoted mod z, okay, and it's defined as mod z equals square root of z bar. Of course, positive square root. Whenever you write square root, it's positive square root of z bar. And clearly you can see from here that that is equal to square root of x squared plus y squared. Okay. So of course, if z is real, absolute value of z becomes the absolute value of x, right? So this is sort of like absolute value in the reals, but in the complex numbers, it gives you a different sort of length measure to a complex number z. Okay, so these two things are sort of they come about because of the having two real numbers in the definition of complex numbers. Now we look at division. Division is of course possible only when the denominator is not equal to 0. A plus bi divided by c plus di. The trick is to multiply and divide by the conjugate of the denominator. Okay, so once you multiply and divide by the conjugate of the denominator becomes real. Okay, c square plus d square becomes real. So in the numerator you just multiply, mean ac plus bd here will come out this side. Okay, and then plus bc minus adi. So this is just polynomial multiplication on the numerator, and then denominator, because of z bar, it just becomes c square plus d square. So this again becomes a complex number, right? So this denominator you can divide here, divide there. So you get a real number plus I times another real number. So that becomes a complex number. So division is quite easy to do using these conjugates and absolute values and such ideas. Okay, so this is standard arithmetic with complex numbers. You should be really comfortable with this arithmetic. You'll expect a lot of comfort in doing computations with complex numbers. Okay, so quick properties. These are all important. If you have product of two complex numbers and their whole conjugate, that's the same as z1 conjugate times z2 conjugate, z1 bar times z2 bar. Same with quotient. z1 by z2, the whole conjugate is z1 conjugate divided by z2 conjugate. Same sort of true also with absolute value. Absolute value of z1, z2 is absolute value of z1 into absolute value of z2. Absolute value of z1 by z2 is absolute value of z1 divided by absolute value of z2. And interestingly, you notice that absolute value of z and absolute value of z bar are the same. Z and z bar, a number and its conjugate have the same absolute value. Here's another couple of interesting properties. Z plus z bar is also unreal. Okay, but z plus z bar can be negative, right? We saw z bar is real and positive, I mean non-negative, but z plus z bar can be negative, but it's always real. In fact, these two formulae are very nice to remember. Real part of z is z plus z bar by 2. Imaginary part of z is z minus z bar by 2i. Okay, these are very easy to prove. These are standard. You just write z equals a plus ib, and all these formulae will fall out in your lab. Okay, so these are important facts to remember, and you can use these and do such operations. Okay, so I'm not going to do this in detail for you, but this kind of arithmetic you should be really comfortable with. Multiplying, dividing complex numbers, dividing, adding complex numbers, then dividing, adding, taking conjugate, all of these things you should be really comfortable doing. Please practice, and you might have seen this in your school, but I'll urge you to practice these kind of calculations and not make mistakes. Okay, so now what is really interesting about complex numbers, why they have a special pride of place in the math analysis and modeling and all that, is how they work with polynomials. Okay, so here is the fundamental theorem of algebra. There's lots of fundamental theorems we have seen in this course. So fundamental theorem of algebra, I'll just state it. We don't have the tools to prove it yet, but it's a very powerful, very powerful result. It's extremely useful. Okay, so it starts with this observation. Supposing you have a polynomial with real coefficients, you may not have a real root to it. Like for instance, if you say x squared plus 1, right, that polynomial has no real root. There is no real number for which x squared plus 1 will be equal to 0. Likewise, x squared plus x plus 1 also has the same category of things. So, I mean there is no real number for which x squared plus x plus 1 will be equal to 0. However, these two examples have complex roots. You can see that these are quadratic equations. You may also know how to easily solve them. So, x squared plus 1 has two complex roots, plus I and minus I. You can substitute that there, if you put plus I squared plus 1 is 0. Put minus I squared is anyway I squared, right. So, I squared plus 1 is again 0. So, x squared plus 1 has two complex roots, no real roots, but two complex roots. Same happens with x squared plus x plus 1. X squared plus x plus 1 also has two complex roots, and you can use the quadratic roots formula very quickly to see that minus 1 plus or minus root 3i by 2 is in fact a 0, both the two zeros of x squared plus x plus 1. Okay. Now, what about any polynomial? These are just quadratic, so I could just show you the roots. What about cubic polynomials? What about quartic polynomials, quintic polynomials, polynomials of degree 272, right? There can be any number of polynomials. What can I say about their roots? Okay. Clearly, they may not have real roots. I know that for sure. What can I say about their complex roots? So, here is where this powerful fundamental theorem of algebra comes in. It sounds very simple, but it is a really strong statement. Okay. This is the fundamental theorem of algebra. Any non-constant polynomial with complex coefficients has a complex root. Okay. That is the first line. Okay. So, just now I showed you there is a polynomial with real coefficients that does not have a real root. Now, that cannot happen with complex numbers. Any polynomial you take with possibly even complex coefficients. The coefficients can also be complex. In most cases, we look at real coefficients, but coefficients can also be complex. Any polynomial, as long as it is non-constant. Why should I say non-constant? So, it turns out 1 is also a polynomial, right? Polynomial of degree 0. 1 won't have any roots. Okay. Anything that is non-constant, which has complex coefficients, has a complex root. Okay. So, this statement sounds like I am guaranteeing only one root, but that is enough. Why? The reason is, if you have one root for a polynomial, you can factor one, supposing a is a root of a polynomial, x minus a becomes a factor of that polynomial. So, it can factor out. So, the polynomial can be written as x minus a times something else. Okay. So, that something else will have degree less than the original polynomial. So, you repeat the same result there, you will get one more root for the factored polynomial, and then you get one more root like that. So, basically that first line guarantees the second line. So, a degree n polynomial has n complex roots. Now, what do I say? Counting multiplicity, some of these roots may be repeated. Okay. You may have the same root appearing again and again, that is okay, we do not know, we do not have control over that. But so, because every non-constant complex polynomial has a complex root, you are guaranteed that you can find n roots using this method of repeatedly factoring and finding. You may find the same root twice, that is okay, that is allowed, but generally you can find n complex roots. Okay. So, that is the power of fundamental theorem of algebra. The proof lies in complex analysis and things like that. It is fairly advanced. If you do a course in complex analysis, you will see it later on. Okay. Now, more than the proof, for us computing is interesting, and today standard Python tools like NumPy have a roots module. So, this one the statement here, I am importing NumPy and I am calling np.roots. Roots is a module or a function function in Python NumPy which will compute the roots. Now, what is this? This just codifies the coefficients of the polynomial. Basically, it says 9 is the constant, 7 is the coefficient of x, 3 is the coefficient of x squared, 4 is the coefficient of x cubed, minus 1 is the coefficient of x power 4, 2 is the coefficient of x power 5, 1 is the coefficient of x power 6. So, this is a 6th degree polynomial, x power 6 plus 2 x power 5 minus x power 4 plus 4 x power 3 plus 3x squared plus 7x plus 9. This is a polynomial of degree 6, and you just call np.roots, out come all the roots of this polynomial. Okay. So, you see there will be 6 roots, the first root here, second root here, third root here, fourth root here, fifth root here, and the 6th root. So, there are 6 zeros or roots of this polynomial, and you see 2 of them are real. This one is real, this one is real. Okay. And then you notice there are complex conjugate pairs. This one is a root, and the conjugate of this guy is also a root. okay, right. Here is a root and the conjugate is also a root, okay. Okay, so this is not surprising, right. So this polynomial has real coefficients. So any polynomial that has real coefficients, if it goes to 0 for a complex number z, I can take conjugate on that whole expression, and you can easily show by the properties of conjugate that if z is a root of a complex polynomial, of a real polynomial with real coefficients, z bar is also a root, okay. So you only have to find one complex root, the other complex root, the conjugate comes for free, okay. So that's a very nice statement you can prove. Well, I'll leave it as an exercise to you. You show that for, it's very easy to show and see. So you see that these two are complex conjugate pairs, these two are complex conjugate pairs. Of course, if the root is real, the conjugate is itself. So you don't get anything new from this. So you have 2 real roots and 4 complex roots, 2 complex conjugate pairs, okay. So this is something, this is a very, very useful property, a very nice property that you can remember, okay. So we saw real quick some arithmetic with complex numbers. The arithmetic itself is easy, but the real power comes when you think of polynomials with real number coefficients or complex number coefficients, and the fundamental theorem of algebra gives us this really powerful result that roots are available in the complex numbers. Thank you very much.